Prof.VenkataKrishnan. Postgraduate doctoral education in IIT Kanpur, and his professor, Dr. He was later chaired by the director of IISER Trivandrum, Professor J.N. Murthy. He's a very well-known synthetic organic chemist. After his PhD, he had his postdoctoral experience in Germany. You were in Germany for some time, right?
France.
France. You went to France for a few years. And when we had him join, I believe it was 2006 or 2007, around that time. 2006 batch, right?
Joined for 2013.
Oh, 13, much later,
Yeah,
much later, 2013 batch. I mean, he has been very close to me, and he has been my neighbor until about 2 months ago when I was kicked upwards to go to the second floor building. Until then, I was on the ground floor, and he used to be my neighbor. So we used to talk science, and also he helped us in building an international program on environment with 3 universities, IIT Madras, Thailand, and also Singapore. Is the overall coordinator of general environment, sustainable environment or sustainable biology. I don't know the exact title now. He did the particular course now. It's the 2 semesters he has done. And he has been very, very well known as a lead organic chemist. And one of my students also worked with him on some computational aspects in understanding the geometry of the molecules and the compounds that he synthesized. So in that sense, I know him as a very serious and very committed organic chemist, and an extremely polite and smile. He has, by knowledge, I have not seen anybody with anything other than only smile. He's the only one. And he will be very happy to give you 2 lectures, one now and one after lunch. Feel free to interact with him, ask him questions. He likes Shankar Raman and like my other colleague, Balaji. These are all extremely well-known organic chemists in both India and abroad. So you have the opportunity to interact with some of them. Please take this and continue to keep the contact later if you want to. Give me that. So, Balaji, you are right at the regulation. You are talking about fluorescent macro science. Thank you. Go ahead.
Very kind introduction. Actually, senior professors are our role models. So, he's one of mine. Before I start, I came to know that you are all from various colleges, mostly university affiliated, right? And all are from Tamil Nadu. In between, if you don't understand, please feel free to ask me. I can even if you could not follow. Which one you are comfortable with? Tamil or English? Both are okay. Fine. So we will do both. Do mixed class. Good. So yesterday and you had lectures yesterday also. Some organic topics were discussed. NMR up to what stage?
Variable temperature.
Variable temperature NMR. Starting from basics or only variable? Only variable temperature. Okay. And aromaticity is discussed also. Conformational analysis, have you ever been taught of? You have studied in your MSc? So you are all second MSc students? All are second MSc. Any from first MSc? There are few. But you must have studied conformational analysis in the BSc itself, correct? My understanding is correct. Right? So we will see, so I am going to just give you some information on conformational analysis and how you use the conformational analysis to rigidify certain systems, which can have implications in molecular sensing or molecular recognition, right? So those kind of applications. So conformation analysis is a fundamental topic. You must have studied many times. You would have started with ethane, and then you would have studied about butane, and then propane. How these Gaussian interactions are playing an important role, right? Energy-wise, Gaussian versus eclipsed versus staggered. All that you must have studied. Gaussian is always a high energy conformation, and you have eclipsed is again eclipse is the highest energy, and Gaussian is the higher. Then staggered one is completely low. So this you must have studied. So we will talk about some of these aspects when I am discussing about fluorescent microscopes. Okay. This is a very recent work. I think sir's student is also involved in this project, as sir mentioned here. So I'll just briefly tell you about if it is too much, no, dose, if it is too much of a dose, you let me know. So we can moderate it, so it's not a problem. So the first case, when we talk about macrocycles, the very first example that might have caught your attention is crown ether. How many of you are aware about crown ethers? All of you. All know. Anyone doesn't know about crown? Okay, so all of you know. I assume that all of you know. This is a molecule which was discovered in 1960s. Very old molecule. It was discovered by Feddersen. The main role of this molecule was it is very important to capture certain cations. Correct? So the nomenclature wise, you will count 1, 2, 3, 4, 5, 6 oxygen atoms here, right? And methylene bridges are there. So you call this molecule as 18 crown 6. 18 crown 6. It's very much useful in capturing the potassium ions. So when it captures potassium ions, you will see the K plus sits between all these oxygens, and the shape of that when potassium ion is inside looks like a crown. Okay. That's why it is called crown ether. And if you just take this molecule and put it in solution, it will not be in crown. Correct? Because these methylene bridges and the oxygen would go or do all these conformational motions, and they are no longer crown. But the moment this potassium ion sits inside, everything becomes rigid, and the shape of it actually behaves like a crown. That's one of the reasons you call that as a crown. So all these macrocycles are meant for a purpose. The purpose is very simple, and they should have a molecular recognition property. In this case, crown ether case, it is a cation, which is potassium ion, and macrocycle is this crown ether. This is the first part that the macrocycle should exhibit, which is molecular recognition. Second one is the complexation. How does this molecular recognition property come into picture? Via complexation. What is the complexation in the case of crown ether? Oxygen chelates, right, with potassium ion. Captures the potassium ion, in other words. So that is the sensing part. So the complexation should be this. If these two properties are fulfilled by a molecular structure, then the molecular structure you may call it as a macrocycle. Okay, so that is the basic problem. And all these macrocycles or molecules are studied usually under a broad classification of supramolecular chemistry. So whenever you talk about supramolecular chemistry, one of the areas that you would usually see is this macrocyclic chemistry. Okay, so move on to a few other examples. Another molecule is cryptand. Okay. it is a three-dimensional version of ground ether. Ground ether is just like this, right? Flat. But you add one more arm, right? Connecting this heteroatom, then this structure becomes three-dimensional. That is called a cryptan. Crypt crypt means a cage. Okay. So it looks like a cage, and let us imagine that here as well as here you have 6 oxygen atoms only. Correct? Both the cases you have 6 oxygen atoms only. So this can bind with potassium. This should also be able to bind with potassium. But instead of the 2 arms, now it has third arm that is coming into picture. So the chelated potassium is going to be not lost very immediately. Correct? Because there is a 3-dimensional arm that is coming and holding it tightly. So within the space available 3-dimensionally, this potassium ion is trapped inside. So the binding affinity of the potassium, right, is quite stronger in the case of cryptan when you compare it with ground ether. This was discovered again by Jean-Marie Lin. He made this molecule purposefully, and he has shown that the potassium ions can bind to the skeleton multi-fold when compared to that of a simple 2-dimensional ground ether, for which he was awarded the Nobel Prize. Okay. Jean-Marie Lin is one of the persons who was awarded Nobel Prize for developing a field of supramolecular chemistry. Okay. So that is another example. Then you would have come across another macrocycle which is called as cucurbitural. How many of you know this molecule? So this is a cucurbitural. Cucurbit, the name means it is a pumpkin. The molecule, if you look at, has the shape of a pumpkin, right? And kind of say that this portion is like a tape, and you have oxygens on both the upper rim and at the bottom rim. Oxygen are pointing. So this could be synthesized by simple reaction, condensation reaction. You take glycoural, react it with formaldehyde, paraformaldehyde, you will be able to generate this cucurbitural very easily. Now, this molecule has a difference. Peripheral arms, upper arm and the bottom arm, are surrounded by oxygens, correct? But the middle part, if you look at, it is all made by nitrogens and some carbons and hydrogens and so on, right? So if you are incorporating some ions, will it sit outside or will it sit inside? It should be mostly located outside because oxygens are pointing at the outside, correct? So if you have an ammonium ion, let us say, right, or a alkyl chain is there, at the end you have ammonium ions, you will see the alkyl chain is sitting inside the cavity, the ammonium ions, one of it is here and another one is, right. So the middle part, I would say it has a hydrophobic in nature, whereas the upper and bottom rim is a hydrophilic in nature, they are polar, so they can bind with several of ammonium ions. It's a very nice molecule because the inner portion is quite larger and outer side is narrow if you measure the dimensions, okay. So it's another example that has come up in the literature. Cyclodextrins, another class of macrocycles. How many of you know cyclodextrins? Alpha, beta, gamma cyclodextrins, right? Each of them have different cavity size, and they can incorporate guests of different size depending on the cavity size. So you can see alpha cyclodextrin has D-glycopyranosyl units, 6 of them. Beta cyclodextrin has 7 D-glycopyranoside units. Gamma cyclodextrin has 8 of such units, and depending on the number of glucose Pyranose unit, you are having the cavity size also being varied. Now, when you vary the cavity size, you can also incorporate guests of different sizes, right? That is one advantage. It is not necessarily that it would capture only potassium, but if you increase the size, it can also capture other bigger ions as well, or bigger molecules as well, right? So that is the flexibility it gives. So cyclodextrin from 1904 is known. Many applications right now in advanced level application, if you want to say, these kind of cyclodextrins are used in even in column chromatography. You are familiar with column chromatography? Which is used to separate compounds. When you get mixture of compounds, you can load them on column chromatography, develop a separation before that, run it with the eluent. These mixture of compounds would separate and then come out, right? So to modify the properties of silica gel, people have been using cyclodextrins to improve the efficiency of it. So all of this technology has come up very newly, and that is where the role of macrocycles are contributing. Okay, they are contributing in a big time. And this is one of the recent reports. The cyclodextrins have not been used till now to capture any potassiums ions, for example. Okay. So one of the research groups took cyclodextrin, whose diameter is about say 1 nanometer, and they mixed it with some potassium salt. They wanted to see how these potassium ions are getting, whether it is going in or it is bound to one of the hydroxys, right? And what is the type of structure that they can generate. The very first example, I don't know why it was missed. For a long time, this potassium ion interaction with these macrocycles were not studied. This is the form that you get when you mix it with potassium. The purple spheres that you see are the potassium ions, and they form a nice three-dimensional architecture such as this. 6 of these molecules arranged. You will see this one is on the side, another one is on the side, one on the top, one at the bottom, one behind, and one at the front. So there are 6 of them organized very nicely to give you this kind of a three-dimensional architecture. Okay, wherein potassium ions are seated somewhere, these junctions, building such kind of a three-dimensional network. It doesn't stop there. Okay, it further moves and forms kind of a channel. This is another potassium salt of K2PtCl6. Okay. When you mix the cyclodextrin with this K2PtCl6, it forms a very nice one-dimensional structure, wherein potassium also is part of, and such kind of beautiful structures could be generated. This study was done by none other than Professor Stoddard, who also won the Nobel Prize very recently. Okay, so macrocycles play a very significant role in applications as well, not only in molecular recognition, sensing, and other properties. They have been now into biological applications and also chromatography separation techniques, right? All of them macrocycles have captured. After all this, there were a few other molecules that came into picture, which are also macrocyclic. One of that is made by arene units, right? In the previous case, what you saw was all of this, where the backbone was simply by alkyl chain or by some glycouryl units. But let us say this unit could be replaced by some aromatic units. Then you can also incorporate, or it can also sense some aromatic molecules, which could be toxic or explosives and such kind of pesticides, for example. You can trap them into these macrocycles, and that's one of the visions. Okay, so this type of molecule was catching the attention. These are called cyclophanes. Are you aware about these molecules? Right? This is paracyclophane. The typical name for this is 2,2-paracyclophane. And you will also see the other molecule named number 2 here, which is the metacyclophane. And the difference between these two is the methylene bridge connects the 1 and 4 positions of the benzene or both the benzene units, right? Not methylene, sorry, ethylene unit. CH2 connects these two benzene units at via 1 and 4 positions of benzene. Now, how about this structure? Will these phenyl rings be able to rotate, or will they be able to rotate? What do you think? Phenyl ring is like this, right? And they are tied with CH2 units. Now, these phenyl rings, would it be able to rotate or no? Or there is some difficulty, there can be some difficulty in rotation. What do you think? There can be some difficulty in, don't have sufficient space. How about this? This is connected at 1 and 3 positions of benzene. It has a freedom to rotate? Some say no, some say yes. What are the ways by which it can rotate or flip? There can be 2 rings like this, or this can fold and sit on top. Correct, no? These two aromatic parts are like this, connected via the CH2. But now it can be like this, or it can fold, right? Or this can fold up and make phenyl stack. That is possible. So, in this case, you can have different arrangements possible. In this case, well, if you give sufficient chain length, not limit to 2, you have 3 or 4, make it longer, then these phenyl rings could start rotating. So, if you give more conformational freedom, then the molecule would reach it undergoes several rotations and come to a stable conformation. Correct? So, this could be high energy, and here you have the molecule has a choice to do. Either it wants to be one on top, or it could be like this, it has a choice. So, that is the benefit that number 2 gets. And typical modes of bridging, if you want to say, here we talked about 1,4 and here you talk about 1,3. And there are also scenarios you can connect with 1 and 2. That is also known in the literature. People have made that, people have studied. So, fusion at different points are possible, or connection through different points are possible. Depending on the connection, you name them para, meta, orthocyclophane. Right? This is a basic. As we discussed for compound 2, you can have 2 different conformations. You know the difference between conformation and configuration, I suppose. Right? What is the difference?
Configuration is between 2 different molecules. Conformation is occurring the same molecule.
Configuration means it is, you are talking about 2 different molecules, E and Z. These are isomers, so geometrical isomers, but they are 2 different entities. They have different properties altogether, right? But on the other hand, we are talking about conformations, the same molecule having all the possible CC bond rotations, and because of that you generate n number of structures, and all of them are conformations, right? It's like I stand like this, I am still Venkat, I lift my hand like this, I am still Venkat, right? So it is like that. So conformations could be possible for the M cyclophanes, okay? So here 2 examples are given. One conformation, as you saw here, is called as anti, when 2 phenyl rings are opposite. You can have a scenario when 2 rings are one on top, this is called the syn. So you can have 2 different conformers. How can you differentiate these 2? Simply by NMR spectroscopy, because when you talk about benzene ring, you must have studied about diamagnetic anisotropy that is established on benzene rings. So since diamagnetic anisotropy is there on benzene ring, if a proton that comes on top of the benzene ring, you would say that that proton will be shielded, right? And if a proton is away from the benzene, the electron cloud, then obviously what you see is it is going to be d-shielded. So by knowing that whether the hydrogen is away from the benzene ring or hydrogen is pointing above the benzene ring, will be able to help us to distinguish between these two conformers. Again, here what helps is the variable temperature NMR spectroscopy, room temperature, both the conformers are possible. They interchange between themselves very fast, and hence you will not be distinguish these two conformers. What you see is the net average effect in the NMR conditions, right? But if you want to definitely distinguish between these two, then you have to do a BT NMR spectroscopy, right? The technique that sir taught you yesterday, and you using that, you should be able to say how much of anti is present, how much of syn is present in the solution. Because for the syn, this hydrogen is away, so it is in the de-shielding zone. The proton here should appear at delta 6.82 chemical should value. If it is anti, you can see this hydrogen is exactly falling on top of this ring, and this hydrogen will fall exactly under the benzene ring. So these two hydrogens should face a shielding effect, and hence you see the lower delta value, which is 4.7. How much shielding is denoted by the number that you are seeing there. It is an aromatic hydrogen, but the hydrogen is resonating at 4.17 delta. Okay. The peak, whatever you see, let's say both of them are present, right? Then you see peaks at 4.12. You must also see peak at 6.82. The relative integration is going to tell you how much of the population of these two existing in the lower temperature at a particular temperature. Okay. So if you elongate the chain length, you can think of various conformations possible between anti and syn. So a syn has to come to anti, it can go to this and flip back and forth. So this oneness should be happening in the solution all the time in order to equilibrate between the cis and trans. It has to take various geometries to go from one conformation to another and so on. Okay, this is a simple introduction about cyclophanes. You keep this part in mind. We are going to build a macro cycle, right, which is an expanded form of M cyclophane, where all 4 of the benzene units here, all the benzene units are connected via 1 and 3 positions, right? With what you are connecting? You are connecting via a methylene bridge. This methylene acts as a bridge, right? And every benzene ring is connected through 1 and 3 positions. Let us say you made this compound, right, by a simple condensation reaction. This molecule is formed, and you will name this molecule as 1,1,1,1 metacyclophane. And this metacyclophane again is not going to be rigid in solution. They will also have conformational motions, right? So we are increasing the complexity. So most of the arene rings would flip up, flip down, both could be the same side, both opposite ones can be up, opposite ones can be down. So various conformations are possible for this molecule, correct? So such kind of molecules are introduced to the supramolecular chemistry by one Bayer, right? He took a phenol and then condensed it with paraformaldehyde. Phenol reacts with formaldehyde, gives you what? Bakelite, right? Bakelite was a resin, correct? And high molecular weight resin in that form. This is the color of the bakelite that was synthesized in 1872 by one Bayer. He couldn't identify what could happened, it was identified as a polymer, but the person that you are seeing here, Cram, first made this compound or isolated this compound from the resin. Okay, moment polymerization happens, yeah, most of it is gone as a resin. Some portion, by controlling the polymerization extent to form an oligomeric cyclic product, right? Lot of optimization was done by this gentleman. He isolated a soluble compound for which he got the crystal structure, which turned out to be this. Okay, and the interesting part here is he did not take the perfect phenol. Instead, he took a para-substituted phenol. The para position of the phenol was simply tertiary butyl. Polymerization, if it happens on phenol, it should happen through the ortho and the para positions. Correct? Condensation reaction is initiated, so it forms cross-linked network polymer, which you call it as backlink. Let's say you block one of the positions, then what you get is only both the orthos are available, and when both the orthos are available, well, you still have not avoided the polymerization, but you have decreased the extent of polymerization. So that extent is also resulted in this kind of a macrosite. So you have 4 of the tertiary butyl phenol units attached, all of them were connected by methylene. Because you have brought in all the hydroxy units here, they form intramolecular hydrogen bonding and gives you a nice crown type molecule, crown type structure. Okay, and this is quite soluble because though there is hydroxy, 4 of them, molecule is supposed to be very polar, but you can dissolve it. These tertiary butyl groups are very much helpful to solubilize it in a solvent. He could crystallize it and tell that, look, this is the molecule I got and this is a crown shape molecule. Again, this gentleman got a Nobel Prize. Okay, so this structure puzzle was resolved. You see, it is done in 1872. The structure resolved after 100 years. Okay, so that much research is going on onto such molecules, identifying structures, appreciating the nature. So he got this molecule. Now, what is the advantage with this molecule? Because it has a nice crown type structure, the inner part of it is vacant. It is available for any guest to go in, come out, put a new guest, it can come in and go out. You can do this process on and off, right? So this is the advantage. It was further built by Gakshe, David C. Gakshe. So he made using resarcinorenes. He built resarcinol, he took resarcinols instead of phenols. Resarcinol has 2 active positions here and here. This is ortho to this is para to this. Similarly, you have 2 active positions. You can do the same condensation reaction with paraformaldehyde or probably any aldehyde for that matter, aliphatic aldehydes, aromatic aldehydes. All the alkyl chain comes in here and all the resarcinol units are arranged nicely, right? 4 of the resarcinol units can come together to form a macrosite. Now in this case, what you will see is the crown is something like this. You keep all the hydroxy units are pointing upwards, right? And the alkyl chains are pointing downwards. In this molecule, you see the alkyl chains are pointing upwards and the hydroxy units are pointing downwards. So this, through the bottom part of the hydroxy units, this gives the crown shape, but here the intramolecular hydrogen bonding established between the top hydroxy units, it gives you a crown shape. This molecule is not conformationally flexible. If you put a long alkyl chain here and block it, this molecule cannot be conformationally flexible because 4 of such hydrogen bonding units are present at the periphery, making this molecule quite open. Okay, so design wise, there are differences, but each has a uniqueness to exhibit. Okay. Next, in 2008, very recently, another scientist reported a pillar arene. Instead of using 1,3-dihydroxy in the case of resorcinarine, he used 1,4-dihydroxy benzenes. Again did a simple condensation reaction, right? And that formed macrocycle wherein the arene units are tilted. You will see the hydroxy units are pointing upwards and the other hydroxy units are pointing downwards. So they behave like pillars. There is no crown type shape. Okay, they are like this. So they are called pillar arenes. He named it Ogoshi, a Japanese scientist. He made this molecule and he named them as pillar arenes. Then afterwards, dissymmetry is introduced into the macrocycle. Instead of starting it with resorcinarenes, he simply started with methoxyphenols. McGillivray was the person who made this molecule. Methoxyphenols were the starting materials. He did the condensation. So you got tetramethoxyresorcinarine molecules. If you look at this structure, it is a racemic molecule because these hydroxy units along that way, if you point out, one could be clockwise arrangement, another one could be anti-clockwise arrangement. So it is a mixture of enantiomers. When you get it, this molecule as such is existing as a racemate. There have been lot of efforts to separate them, right? By appropriately functionalizing them, form diastereomers, separate them, all of that people have done, and you can generate chiral systems out of this. Okay, so this symmetric resorcinarenes were the first report by McGillivray and group. So there are a lot of evolutions. All of these structures are very, very important in supramolecular chemistry. Nowadays they have been explored in separation techniques because they are very polar. You can use these molecules in separation or recognition. Few other classes have come. Now that you have list of molecules in hand, you can play around with the aromatic units that you have put in. You can replace the simple arene by a heteroaromatic arene, right? Likewise, people have made developments. In that case, pyrrole has been used, pyridine has been used. You can also see imidazoliums, you can also see indoles, you can also see benzofurans. All that analogues have been tried. And they have made various heteroaromatic arenes as well, macrocycles. Okay, to call them as heterocalixarenes, the calixarene, resorcinarine, pillar arene, and so on. So it is a simple analog of this where the central aromatic part is now replaced by heteroaromatic. You call them as heterocalixarenes. There are some other examples. You still have the benzene rings. They are calixarenes, parent calixarenes. Remove the CH2 by some heteroatoms. So there is no CH2 connecting the aromatic units or the phenolic units. What you have here is a heteroatom. Probably they are nitrogens, probably they are sulfurs, probably they are oxygens. These kind of macrocycles are called as heterocalixarenes. Terminology wise, O we said previously hetero, and this is heterocalixarenes. People have made various such systems having heteroatoms that connect these aromatic groups. Okay, so there are different variants that are existing in the literature. All of this except the hydroxy ones, right, are known to undergo conformational motions. So you dissolve them in solution, you want to record an NMR spectrum, you will get actually the averaged signals in the NMR spectrum because they are rapidly undergoing conformational changes. And you will see a lot of such conformations where boat is existing, chair is existing, diamond shape is known in the literature, saddle, and so on and so forth. You can have various conformations possible for these kind of macrocycles, right? And as I said, dissymmetric resorcinarenes were also reported. You can call it as R and S or P and M, right? Two of these enantiomers exist, coexist, and form racemates. And this can also be made, and people have separated. They have put in various applications, and they have. Okay. Concern in this case was that whenever you want to take a phenol, condense it, right? You will also have your polymers along with the polygon. It is always a competition. Okay. So that results in always low yields. You ask anyone how people would synthesize porphyrins in the laboratory. 4 of the pyrroles have to condense with some aldehydes. Right? And yields are very low. People have improved these days, but it is always a competing. There is always a competing polymerization reaction accompanied, and that has to be minimized. Right? Only then you can improve the yields, but otherwise you will always result in poor yields in the synthesis. And then purification is difficult because your oligomeric compound is stuck in between the polymer, so you have to do a lot of strategies. You have to put in a lot of strategies to isolate such pure material oligomeric compound which is soluble, which you can use, which you desire, right? So that is a humongous task actually. It takes lots of time. Whomever is involved in macrocyclic synthesis, you ask them, they will complain about these two. So very laborious synthesis, purification is tough. After sitting in front of the column for 1 day or 2 days, you get only few milligrams. With that you need to do studies, right? So that is quite challenging. Though procedures are evolving with improvements in the yields, but this is a constant problem. Tedious synthetic methods, sometimes you will need harsh conditions to do the studies, right? Synthesis, and multiple regioisomers are possible, like we said. If the active positions are not blocked properly, you can get various other isomers, regioisomers. That also diminishes the yield to a considerable extent. What was lagging in all these cases is the photophysical problem. You see all these macrocycles that we got, we simply have benzene units or some small heteroaromatic units. These do not have excellent optical characteristics. For example, you want to study some absorption with these molecules. You want to sense these gas using fluorescent spectroscopy. All of that is not possible because these are simple units. Both will have absorption and emission in both the absorption and emission will happen for these units in the ultraviolet range. So even if anything it gets incorporated, it is very difficult for you to look at through your naked eye. You cannot identify. So you need a spectrum photometer to identify, and otherwise you have to rely on NMR spectroscopy, which is an expensive technique for every universities to have. So these are certain challenges associated with these kind of molecules. Okay. So what we thought was, okay, we first do a search in the literature. We find out what kind of structures people have exploited. Always we found that there are resorcinary kind of macrocycles which were taken, and always some fluorescent molecules are attached to them. Okay. So that means what? You have to synthesize the macrocycle, you have to appropriately functionalize them, then you want to attach these fluorescent units onto the top. So it adds extra synthetic steps, right? Well, but it still solves the purpose of sensing. If any gas molecule goes in, these fluorophore units that are just flanking at the periphery would detect the gas that is coming in. It can send some signal, correct? Oh, gas is coming in, so it is trapped into this cavity, so it can give a signal. So you can monitor those signals carefully using spectroscopy techniques, and you can say, okay, there is a gas incorporated into the cavity. But all these modifications would need additional synthetic steps at the expense. You need to do that. So getting a small quantity of the compound, poor yields, and you want further functionalize, that is again a problem. So we need to again come up with a new method. So this is a common strategy that people have employed. What we thought was in our laboratory, okay, we have heteroarenes which people have already used. We saw about pyrroles, we saw about benzobifurans, benzobithiophene, right? All of them have been used. But what we want to know is, okay, one of the heteroarenes, let's say, it's fluorescent. We take the heteroarene itself, fluorescent heteroarene, and then tie them up by standard methods. Otherwise, you have a standard unit to which you functionalize it, and ultimately you generate a fluorescent heteroaromatic molecule everywhere. and see you can make a fluorescent macrocycle. That was the idea. So the logic was you take a fluorophore and do this kind of a macrocyclic synthesis wherein 4 of the non-fluorescent units which were there previously are now changed to a fluorescent units. So now the macrocycle can glow. It can just give out light as and when it absorbs the appropriate wavelength. It absorbs and then emits the light. Now let's say if that process happens, you put a guest inside, it will automatically send a signal. Right? Either fluorescence will be lost or something happens to fluorescence which you can sense through spectroscopic method. Okay? If the fluorophoric units give you a visible emission which you can just see, then moment you add the guest, if something happens to the fluorescence, your eyes can immediately detect. Okay, it is captured now, right? So such is the idea that we had. What we thought was a common molecule which is coumarin. Coumarin is a very bio-friendly skeleton, right? Every day in cooking also we use coumarin based molecules and it's bio-friendly. We can put them onto the macrocyclic skeleton. Now because of the inherent fluorophoric nature, these compounds would emit light and if gas goes in, you will be able to diagnose. So molecular recognition aspect can come into picture. As I said, it has medicinal application, it is used in laser dyes and it is used in optical sensors because of their beneficial fluorophoric characteristics. Okay. So it's a good thing to start up. The idea was, okay, initially we said about dissymmetric macrocycles, correct? So synthesized by McGillivray, I said. So you use this skeleton. From phenols, you can use Speckmann condensation reaction to generate coumarins, and you can ultimately, from this structure, you can result in coumarins. The ultimate aim was to get a molecule like this, where 4 coumarin units are present. Okay, this was the basic idea we had, and we want to call it as coumarin 4-allyls. This was the plan. So now let us see how we synthesized this. We started off with this macrocycle. This macrocycle was synthesized by slightly modifying the conditions of McGillivray, where we could get good yields. So we modified it, reacted with Meldrum's acid. Meldrum's acid is a cyclic acid actually. You can treat it with this and you get this half malonic acid. This half malonic acid put into reaction condition 7 using Yerton's reagent, which is a good dehydrating agent, and you can get the intramolecular cyclization happening to get the final product that is result. Okay, so now you have this macrocycle that you are seeing there in quite good yields, which my student has optimized enormously, and it is quite reproducible. We are able to get this macrocycle in good. Now let's see how this macrocycle behaves in solution. Okay, and we can make various alkyl chains. We made with methyl here, R is equal to methyl, R could be ethyl, propyl, butyl, all of that. You can get reasonably good yields. There is no problem. Not only the isobutyl, you can take various alkyls and student has made. Now when you look at the NMR spectrum, what you see is a very clear cut signal, right? All of them saying that it is a C4 symmetric molecule, correct? Look at that, everywhere you have C7H, C3H of the coumarin, hydroxy group is somewhere here, broadened, all the signals are matching, it is quite very symmetric molecule, right? Mass also confirms that 4 of these coumarin units are there, all of that is confirmed through mass spectrometer, and it looks like they are already existing in crown, in this shape, right? But when we did the variable temperature NMR, as you see for cyclohexanes, right? I think Sir must have showed this yesterday. Cyclohexanes axial and equatorial positions, which otherwise is a single peak, up to -49, slowly starts to split, right? Giving 2 different signals, one for axial and another one is for equatorial, at close to -90 degrees centigrade. So you can even differentiate these two hydrogens, one in axial, one in equatorial for cyclohexane. Similarly, when we varied the temperature from 25 to 90, 25 you see that as a very average signal symmetric conforming C4 symmetric conformation. If you lower the temperature, you see this signal splitting into two. Then we said, oh, it is not in C4 symmetry, but in solution they are in rapid equilibrium. One is in this form, which we call it as boat form. This would quickly equilibrate to another boat form, wherein these two red arms are up and these two black arms are flat. So this movement is very rapid in solution, but NMR could not see this rapid motion, and hence it sees something like an average. Because you will see at some point when these two arms are up and these two arms are opening up, and these two arms are coming in, you will have a time frame where these two are appearing like a crown, and that is the time scale that NMR figures. So you have an averaged conformation which is a C4, and that is what is denoted at room temperature, but at lower temperature you are able to see these two conformers clearly getting resolved. So two forms at lower temperature. We also did a high temperature NMR going up to 105 degrees centigrade to see in case because when you provide more energy to the system, it could also flip inwards, right? Let us say one of the rings here can go into this and come out, okay? Inward movement of one of the rings could give a different conformer. Okay, we wanted to check that. So we went to higher temperatures, but when we went to higher temperatures, the movement again goes fast. Again, it is an averaged conformer, but the cavity that is available is not sufficient enough to do the inward flipping. Okay, that was not possible. So that is confirmed by the NMR signal. But in calixarenes, such kind of incidents are known because the arena arm is small. Okay, let us say you have a small substituent on the phenols, say methyl, right? This inward conformational change is known for calixarenes. But they have also shown that if you increase the size of these alkyls attached onto the calixarene, right, oxygens, you will see that longer alkyl chains or bulky substituents would not allow it to go an inward movement, inward inversion. That is not possible. Okay, so this is same like that. I think instead of the alkyl chain, since we have annulated by a pyranone unit forming a coumarin, the arene unit is quite large and that is not able to get it through the cavity to give you another. So no annulus inversion is observed also. This we confirm. So application of advanced spectroscopy, okay, to similar macrocyclic systems. Right. We thought, well, it's all good, it undergoes conformational motions. Now we want to make it like a crown. The reason being, the old structure that I showed you, I will also show you later, the old structure that I showed you, this one, right? Let us say if you try to crystallize this compound, you crystallize this coumarin 4 arene compound, okay? It gives you one of this conformation only, which means the boat conformation is only crystallized, not the crown. What does that hint you?
Crown is
Crown is a
intermediate. Also.
Crown is an intermediate. So intermediate means unstable, higher energy. Can we say that? Yeah. So from this port form to this port form, it has to pass through the crown transition state. You understand? So because these two arms, like we said, no, NMR sees the averaged one, but the averaged one seems to be crown. That is the C4 symmetric one. But these two are C2 symmetric one. Okay. So from one form to another, one conformer to another boat conformer, if it has to go, it has to pass through the crown, and the crown is a higher energy state, correct? which could be, you may call it as a transition state to one, when it goes from one form to the another form. So it is a higher energy form. Now another advantage of getting this crown is it has a confined cavity. So cavity size is fixed. So then it can have nice guest incorporation. In the board form, these two arms are like this, parallel, right? There is no enough space in between to do any kind of molecular recognition studies, until otherwise you enforce a very strong interaction between these arene arms and the incoming guest. Otherwise it cannot remain open, right? Because they are already in rapid conformational interconversion. But in this case, with this idea, what we thought was, okay, we will tie these arms up. Previous reports, as I told you, by intramolecular hydrogen bonding, these resorption arenes could exist as a nice crown. And people have done also to tie these arms up to avoid conformational motions. Okay? And when you tie these arms up, they always remain as a rigid crown, and a lot of host guest interactions could be done and molecular recognition studies could be. Okay? Oh, we shall stop, no problem. I can just stop here. We can come back and continue if you wish. Okay, so we stop at this stage. Yeah, thanks.